on here, I guess. It's on. Okay, so today's research paper is elastically deformable models. Okay, so what's the aim of this paper? So what they have done, the authors, they have used the theory of elasticity to simulate some elastic models. So they have simulated rubber, they have simulated cloth, they have simulated paper and flexible metals. They have simulated these four things. So they have not provided the code and we don't have a video. So I cannot show you the video now. But let's see the theory part at least. Okay, so first let's talk about what's a parametric curves, surface and solids. Let's talk about it. So the parametric curve, uh, so just think of a curve in 3D space. So first thing we are talking about a 3D space. A curve can be parameterized using a single parameter. So let's call that parameter A. A is, by the way, a scalar value. They have called it A1. In order to parameterize a surface, you require 2D points, 2D, two-dimensional parameters, and for a 3D volume, you require 3 parameters. So they are calling it as A1, A2, A3. And using those parameters, you are converting it to a 3D position. So using this R1, R2, R3. So R1 will give you the X coordinate, R2 will give the Y coordinate, and R3 Z coordinate. Okay, and if you see R1, R2, in short X, Y, Z, the 3D coordinates in space, the Euclidean space, time T. Okay. Okay, so just remember that in this paper, they are calling the parameter value A as the material coordinates, because in the paper, they are mentioning it as material coordinates. They'll use it a lot, many times, but it's actually the parameter value, nothing more. Okay, fine. Now, the body in its natural rest state. Now, what do I mean by natural rest state? It is the undeformed body. So if you see here, there is undeformed body. This is the natural rest state of the body. And when you deform it, this is how the body looks like after deformation. Okay. So the natural rest state, the parameter, the 3D space values in the natural rest state, it is given by X superscript 0, Y superscript 0, Z superscript 0. So XYZ is R1, R2, R3. And over here, they are not giving the time because the time is not present for rest state. So that's the parameter. Okay, so this R0 gives you the undeformed body, the natural state body. Okay, let's proceed. Now, let's talk about the equation. Okay, so let me quickly. Yeah, okay, it's visible, good. Okay, so let's talk about what's happening in the force. Okay, so first force is the dissipation force. So if you remember the dissipation force, okay, so the dissipation force is given by the damping coefficient. I'm calling it as gamma, followed by the velocity vector. So, okay, so this is not velocity vector, I'm sorry. Oh, okay, my bad. Okay, so this is gamma followed by the velocity. The damping, we are damping the velocities. Okay, then comes your potential energy. So the potential energy, they are calling it as epsilon r. So let me call the same. So we know that when we take derivative of potential energy with respect to R, we get the force. And also we are applying external force. So external force, we are applying it on the elastic body so as to deform the body. This is the total force and it should be equal to mass times acceleration. Okay, now mass, since it's a body can be seen as multiple particles on inside the body. We can integrate. So let's talk about not mass, let's talk about mass density. Let me call it as mu. This is mass density. Okay, so again I repeat, a body is consist of multiple small particles and each small particle has its own mass, and that is this mu. Mu is the mass density. Okay, and this is acceleration. So let's go back to the equation. So okay, in the equation you can see that this term goes on the right hand side, this term also goes on the right hand side, and that's how we get this equation. So gamma times velocity plus the potential energy derivative with respect to R, and this is equal to external force. And yeah, this is mu, mass density, and that can come outside, which becomes dabba square R by dabba T square, which is your acceleration. Okay, fine. Now, before I proceed, let's talk about shapes. Okay, so we have something called shape. Shape has a different meaning when I talk about shape in a volume. Then we have shape of a surface, and then we have shape of a curve. So all three have different meanings. Definitely they are connected. Let's start with shape of a solid. Okay, so now let's assume two solids have the same shape. Okay, so let me create two solids first. So this is one of the solid, and let me just rotate it and translate it. So again, even though the diagram doesn't look correct, let's assume both are same shapes. Okay, when can I say both these shapes are same? This is a shape in the sense this has volume. Okay, this has volume. It's not area, it has volume. When I talk about area, let me create this is area. Okay, this is volume. This, let me call it as area, and let me create another.
Your writing is not getting updated.
Q
Because of
Windows. Okay, I'm not sure why. Okay, fine. So this is volume on the left hand side, and this is area. Let's talk about volume first. So in volume, what we are doing is we are going for, let's say this is a point A, vector A. Okay, by the way, this, when I say vector A, this is the material coordinates. And after transforming that material coordinates to a 3D space, so this is that point. R, let's call it better R of A. This is R of A, the vector. Okay, and then let me give a very small perturbation to it. So let's call that perturbation as R A plus delta A. This is a very small perturbation. Okay, so again, since A has lied here, perturbation somewhere will lie very close to each other. it will be very near the perturbation of our A plus delta A. Now, after taking this perturbation, what I want to do is I want to find the distance between them. Let me call that distance as dl. Let me call that distance as dl. After taking that distance, if the distance remains constant over here as well, if the same distance, the distance remains constant, then I can say that both these volumes, okay, both these volumes are shape equivalent. They are, the shape of both these volumes are equal. So the distance, if the distance remains constant, then I can say the shape remains constant of both these volumes.
Not distant. It has to be the vector, displacement vector, because it can get
The,
inverted also, right?
no, I'm talking about distance. Over here, I'm talking about distance. Okay, so again, let's go through it. The shape of the body is determined by the Euclidean distance between nearby points. Okay, sine, I mean positive distance. Sine, nahi.
Sign distance, right?
Okay, there is no sign attached. It's positive. Okay. So as the body deforms, the distance change, and let A again material coordinate, and I give a small perturbation to get a new point. And if the distance remains constant across both the volumes, then I can say that, hey, the shape of both the solids is exactly equal. The shape is equal. Okay. And now comes, how did they come up with this formula? Let's see. Okay. Uh, According to me, this should have been dl square. I'll prove it now. They have not proved it in the paper. I'm doing it over here. They have not shown this formula in the paper. Okay, so let's quickly prove it. Let me prove it quickly. So if I say, let's say the change of A plus delta A minus R of A. Okay, so now I'm talking about the vectors. Okay, I'm talking about this vector.
Makes sense.
Okay, this, let me call it as delta R. Okay, this we know that should be given by the Taylor's expansion as partial derivative of R with respect to the first coordinate A, let's say 1, or let me call it AI times delta AI, whatever change I have made across that material coordinate, plus partial derivative of R with respect to, let's say, AJ this time, times delta AJ, and so on. So if, let's say, for a curve case, we only have A1. For volume, we will have A1, A2, A3 because it is parameterized by 3 parameters. And for surface, it will be A1, A2. That's it. Okay. Now, delta R, we got the delta R vector. If I want to find the length, we know that I can take dot product. Delta R dot with delta R will give me the dot product. So it's like I'm taking summation delta R by delta AI, summation over I can vary from 1 to 3, dotted with again delta, delta AI, dotted with delta A. Again, I can use the same variable, or let me change the variable, let me call it J. But again, I will vary from 1 to 3 for solid. J will also vary from 1 to 3 times delta AJ. So this is the dot product of these two vectors. Okay, the dot product, if you expand it, you can see that you will get something of this form. This delta, okay, by the way, the word delta which I was using has been replaced by small d. I was using delta, the variable delta, but they have used d. Okay, so if you expand that, you will get this. And this Gij is again, if you see, it's taking a dot product. By the way, coming back to my notes,
Is
Do you want
this
me to
scalar or
expand it,
vector?
or
It's fine, but is this scalar or vector?
it's a scalar? It's a scalar quantity. Okay. So yeah, dot product delta will give you delta r square. And since they are using it as dl, they are calling the length as dl. So it becomes dl square.
But
And that's why I told you that according to me, this formula should have been dl square and not dl. Again, it's according to me. Yeah.
why is this a matrix? If you are saying they are right there, it's
Okay. Now why it's a matrix? Okay.
it's
Let's
a dot product, right?
this this
Second equation, third equation, equation
yeah,
three.
this is a scalar quantity. When I say the scalar quantity, this is the scalar quantity. Okay, this is the scalar quantity. I'll talk about it. Yes. So now there is ij. Now what I can do is I can, so let's talk about a volume. For volume, ij can vary from 1 to 3. So what we'll do is, let's get back to, when I take dot product, I can take dot product between a1 a2. So let's say a1 dot it with a2, then a1 a3. So first thing will be, sorry, a1 a1, sorry. So first thing will be a1 a1, then a1 a2, okay, and then will be a1 a3. Then comes a2 a1, a2 a2, a2 a2, a2 a3, a2 a3, and then comes a3 a1, a3 a2, a3 a3, and so on. Okay, and then this gij represents one of them. So this gij, if let's say gij is 1 2, so then I'm going for the first row second column, so I'm taking this and multiplying it with the delta components and adding it, and then finally it becomes a scalar. Okay, even though I'm saying gij, G is a matrix, again I repeat, G is a matrix, but when I say Gij, I'm taking the ith row and the jth column value and multiplying it with some other scalars and adding all of them to get my final dl, which is the distance. And now comes the shape definition. If the shape, in short, if the distance across all points, if they remain constant for both the shapes, then both of the shapes are equivalent for solid, the 3D volume. I'm talking about 3D volume. Okay, and this definition, they have taken it from differential geometry book. So if you want to study about differential geometry, then there is a Keenan Crane's book. He has taught discrete differential geometry. You can go ahead and read about it if you want to. Okay, now let's talk about what's the shape of a surface. Okay, so I'm calling this G matrix as the metric tensor. I'm calling it as metric tensor. Now let's talk about what's going to happen in surface. So in surface, I'll show you what's happening here. So these are two areas. So over here, I have shown you two areas. Okay, I've shown you two areas over here. When we talk about surface, what's happening is, even though if let's say the distance remains constant, but both the surfaces are not same, because it could happen the curvature of the surface could change. So again I repeat, if you see here, the distance remains constant for both. If you see, both the distance remains constant, but both the surfaces are still not the same. What happened was the curvature got changed. So you can think something like this. So if let's say there's some curvature like this and there's some curvature like this, so the distance between both the points is exactly the same when looked at the differential level, the distance at the differential level is the same, but you can see the curvature is not the same. The slope, if you can see, the slope is not the same. Okay, so for surface, we have to ensure that the G tensor which we calculated should remain constant, as well as there is another thing we have to look for curvature. The curvature should also remain constant. If both of them are exact, so G and B, if both of them are equal for all the points at differential level, then we can say that both the surfaces are exactly equal, are shape equivalent. Okay, now let me talk about curvature. What is curvature? I mean, definitely you all are from uh, mechanical background, so you may know. I'll just quickly give you a basic definition of what a curvature is. Okay, so curvature. Let me draw a curve. Let me give some tangent. Let's say at this point tangent, and at this point tangent. By the way, just look at from differential level. Even though I have it's a curve far behind from far behind, but look it from differential level, very small curve. Okay, now tangent, it has some slope, and this tangent has some slope. So what curvature says is that it is the derivative of tangent with respect to x. It's the rate of change of tangent, the slope of the tangent with respect to x. So if you, now you see the slope, can I say the slope is changing terribly? So this theta versus, let's say, theta 1, and this is theta 2. Definitely there is a big change of theta over this differential element. If there is a big change of theta over a very differential element, then the curvature is high, else it is low. So for example, this one, for a straight line, at this point, the line itself gives you the slope. At another point, again the same slope, you will get the rate of change of tangent becomes zero, and that's why the curvature of a line becomes zero. Okay, fine. When I talk about curvature, so don't, it's like taking derivative of tangent, and tangent itself is a derivative. So that's why it becomes double derivative. And that's why we talk about double derivative here. Okay, so when we talk about curvature tensor, we are actually talking about the derivative, double derivative. And then what they have done is, after taking the double derivative, they are projecting that double derivative onto the unit normal of that surface. So every surface has a normal vector. That differential surface has a normal vector. They are projecting that curvature onto that unit normal, projecting, and that projection, it's the dot product. Okay, and that's how we are getting this Bij as a scalar value. Again, I repeat, this Bij is a scalar value, but when I talk about B as a whole, it becomes a matrix. Okay, we are taking again derivative with respect to A1, A2, A3. Again, the same matrix will get created. Okay, so now if both B and G both are same for two different surfaces, B and G both should be same. In that case, the shape of both the surfaces are equal, but then both should be equal, B and G both. That's the sufficient condition now. Okay, now let's talk about shape of a curve. Now when we talk about curve, we have to look for the curvature, the length, which is the G matrix, the B matrix, and then there is something called torsion. Let's talk about what's torsion. Okay, by the way, when I talk about this length, this is the G matrix. The G matrix over here is 1 cross 1 because it has only one parameter, A1. There's no other parameter. It's a curve. That's why it becomes 1 cross 1 matrix. Similarly, the B matrix has become 1 cross 1. The torsion will also be 1 cross 1 matrix. Okay, but for a surface, G is a 2 cross 2 matrix, B is also 2 cross 2 matrix, and for a volume, G is 3 cross 3 matrix for a volume. Coming back to shape of curve. Okay, so let me talk about what's torsion. Again, you will know because you are from mechanical, but let me quickly cover what's torsion. Again, I'm just giving you intuition about torsion. I'm not covering torsion in detail. If you want to know in detail, Keenan Crane's book will help you. So Keenan Crane has a formula for calculating torsion in his book. Okay. Let's quickly cover what's torsion. So let's say this is a rod. By the way, this rod definitely has some the radius, but consider it as limiting radius. Limit tends towards zero. The radius limit is towards zero, such that it becomes a curve in space. Okay. Now, what torsion means is that keep this. Let's say you're keeping the left end point fixed. So this is fixed, and you are twisting. So you are giving it some torque. While giving the torque, ensure that the cross section area of this rod remains constant across the entire length. So across the entire length of this rod, I shouldn't say rod because it means rigid body, but consider this rod to be flexible rod. Okay. Such that you are twisting it, the cross section area of this entire rod remains constant across the entire length. Okay, so you are just twisting it, the cross section should remain constant. Okay, so this is the cross section area. So it should remain constant across this even after twisting it. So even though after twisting it, if you see the curve or the rod remains same in the limiting factor, but the shape is not the same as per the differential, because as per differential geometry, you have actually changed the orientation of that curve, even though the curve looks same. Okay, even though, so even if I rotate this, so earlier, let's say this is the vector, after rotating, the vector went over here. So you rotated it by, let's say, theta. You rotated it by theta, the vector got rotated. Okay, now my thing is that, hey, the rod remains same visually. Visually the rod remains same, yes, I agree, but when it comes to orientation in geometry, the orientation got changed. From geometry perspective, the orientation of the rod has been changed. So what differential geometry says is that, hey, even the torsion, it means the angle, should remain constant. So that's why when length, curvature and torsion, if all three now are constant, all three tensors, all three are, by the way, 1 cross 1 tensor, you can call them scalar also. Let me call it as tensor for now. Okay, it's a 1 cross 1 tensor, all three of them. Okay, even though if all three are constant for both the curves, then both the curves are shape equivalent. Okay, fine, let's proceed. So I have given you the definition of shape equivalency. Now we can start creating potential energy across across all three shapes, all three volume, shape, surface and curves. Okay, so one basic definition of potential energy: the more the deformation. So if you see the deformation is larger, then the potential energy is high. If small deformation, the potential energy should be low. And if this, oh, by the way, this is the natural shape, the undeformed shape. And if you are just performing a fine transformation, I shouldn't say a fine transformation, let me call it as rigid body transformation. If I'm performing some rigid body transformation, now what do I mean by rigid body transformation? Rotation and translation, nothing more. Okay, affine transformation is not rotation translation, it is much more. So if you are performing rigid body transformation, then it's not holding any kind of potential energy inside it. So any rigid body transformation should lead to zero potential energy. But when you are really deforming it, if the deformation is small, the potential energy is small. If the deformation is large, the potential energy is large. Okay. Okay. Now let's convert that potential energy to strain energy. So it's just strain potential energy. What we can do is that let's call this the G matrix which I talked about. Let's call it the G0, which represents the G matrix for natural's body. Natural body means the undeformed body. Let's call it as G0. Okay, so now for sure I can say that the difference between the G, which is deformed G, minus the natural G, undeformed G, the difference of that, if I take alpha norm, alpha could be anything. Okay, if I take the alpha norm for G and for B, the curvature tensor, again if I subtract, B naught is the natural, the undeformed B, and B is the deformed B. Okay, if I take the difference and go for the beta norm this time, then integrating it over the entire body, if I integrate it over the entire body, this will give me the potential energy inside the body. Okay, this is the potential energy, and similarly this is for the curve. So again, S curvature, S is the arc length, the length, the 1 cross 1 length, okay, the 1 cross 1 length tensor. Okay, yes. Then the kappa is curvature, then this tau is the torsion. I'm taking the difference, squaring them, and alpha, beta, gamma are the amount of resistance to be applied. So if let's say if alpha is more, then you are giving more importance to this change of length. Okay, then beta, if beta is high, then you are giving more importance to the change of curvature, and so on. Okay. No, where is for this curved surface? Okay, where is for? Okay, I guess I missed it for the solids. Let me go back to my the PDF. So yeah, this is the for the solid, the potential energy for the solid. Okay, I missed it somehow. Sorry for that. Let's proceed. So now, so we have calculated the potential energy, but now if you see, it is in integral form. Okay, we are integrating over the entire body. So the body could be again 3D, 2D, or curve 1D. The body could be anything. So we are integrating over the entire body and calculating the potential energy. According to me, again, it's just according to me, there should have been a factor half. Why? Because when I have considered a point A, from A I am going dA distance away, right? And calculating. So again, I could have gone over here, and if I calculate dA, I'm coming back to the same point. So 2 points are being calculated 2 times, if you see. So if you want, I can show it on diagram. Let me go back to my, okay. So let me show it via diagram. So let me create two surfaces. So I'm taking a point A, and this is A plus dA. So I have considered these 2 points and calculated the distance between both of them, or the curvature between both of them. Now I could have actually gone over here and calculated plus dA this side.
Yeah.
And if you see, so both the same 2 points are the potential between these 2 points are calculated two times. So that's why there should have been a factor half here. But again, I could be wrong. Okay. But according to me, the factor 2 should be present. And for that, let me go to the next slide. The factor 2 should be present because after taking the derivative, this 2 and that half gets cancelled. After taking derivative, this 2 and that half which I said gets cancelled, and the formula proceeds. Okay. So let me quickly tell you how they are simplifying. Okay. So they have taken the difference between the deformed G and the natural G. They are taking the difference. By the way, this is called Frobenius norm, if you have heard of it. Okay, so they are taking the Frobenius norm. Since it was 1987, maybe the Frobenius norm was not derived at that time. Maybe.
Okay. Name doesn't matter.
Okay, but yeah, this formula is acting as the Frobenius norm. Okay.
It's not actually Frobenius norm, right? Because there is eta ij. That way.
That's taking the weights
Yeah, but per element weight. But in
per
Frobenius norm, we
element weight.
don't have
Yes,
per element weight.
yes. Okay, I'll take that. Okay, so they are taking per element weight in eta ij, and this is she ij. So they are taking per element weight. But I feel we could have done it with the Frobenius norm.
No, I don't think
No.
so.
Okay, fine, fine. I'll take it then. So maybe it's not Frobenius norm. Okay.
These are metrics, right? Also, these are scalars.
Scalars. Now,
Then
since
it's
I'm
not.
talking about ij, it's a ith row jth column, so it has become scalar now.
So it's not Frobenius norm.
Uh, but we could have converted it to Frobenius norm. I'm just
Then you
saying.
can't have the four factors, right? Eta ij.
Okay. But I'll get back to you on this then. But as of now, it is element-wise subtraction and squaring it as of now. Okay, and then there is integral. And as of now, just for now, let's call eta ij and shy ij. By the way, this symbol I'm calling it as shy. I don't know what you will call it. I'm calling it as shy, xi, shy. Okay. So eta ij and shy ij, I'm calling as of now them as weighting functions. But later I'll tell you what its physical significance is. Okay. And now comes your calculus of variation. So I'm not well versed with calculus of variation, so I'm just assuming this formula is correct.
Yeah,
Okay.
one thing. Frobenius norm was introduced in 1887.
E- e-
1887.
1887, no,
No, no, exactly 100.
100 years ago. Okay. Fine. Now, with the help of calculus of variation, they are performing this trick. Again, I'm not well versed with calculus of variation. So what they did is they converted this entire integral, got removed, and it is now just summation with some partial differential equation. Okay. Now again, I'm not well versed with calculus of variation, so I'll not comment anything on it. Okay. And if you see, there is alpha ij and beta ij, so they have given us what alpha ij means. So alpha ij, if you see, it is in the terms of eta ij and the G matrix, the values of G, and beta ij is in terms of psi ij and bij, the curvature tensor. Okay.
So basically,
Yeah.
what they have done is taken the so force is defined as the gradient of potential, right? So
Yes.
and integral has been converted to the discrete summation.
Yes.
So they have just simply discretized it and converted into force. And
Okay,
for
over here I'll tell you what's happening. Okay, so if you see, the integration variable is dA1 and dA2, so A1 and A2, and then we are taking derivative with respect to R, which itself
is
is a function of A1 and A2. Okay, r, I've shown you, right? R is actually a function of a comma t, so that a comprises of a1 and a2 in scalar forms. Okay, so while taking derivative, I tried to apply the existing Lagrange Euler. If you remember the derivation of Lagrange Euler equation, I tried the same over here, but it didn't work out the same way. Okay, so that's why I'm just assuming that this works. Okay, I'm assuming this works.
And where the integral has also gone.
The integral has gone, but in Lagrange Euler also the integration goes away. It becomes zero. The earlier, if you remember, it is, or let me,
Because that does not go away. That basically it becomes something integrated over a domain. So some factor or integrated over a domain.
which is
And
equal
when
to
you want
zero.
to make it, when you want to make it zero, then you ensure that that something is zero. Then you get this equation.
Right, that something is zero, right? So that at least at the end that integration symbol goes away.
Just to, it's just integral of sum of all elements is zero means every element is zero.
Every element is zero.
Positive element.
Yes. So same way I tried over here, but it didn't. Okay, the same trick I tried to apply over here, but that didn't work out here. Okay, because it was actually because of, since there are two variables in the integration, but when I derived my Lagrange Euler Lagrange equation, there was only one variable in Euler Lagrange, but over here there are two variables. It's integrating with a1 as well as with a2. Okay, so again, I'm not sure how they have proceeded, but I'm assuming it's correct. The formulation is correct. Okay, they have not shown it in the paper how they have derived. Okay, and let's assume again, I'll say let's assume, but now if you see the entire integration has gone, it becomes a partial differential equation. What they are doing is they are converting this partial differential equation using FDM. They are discretizing it, and then they're applying symplectic Euler to for time integration, and that's how the entire story proceeds. Okay, so I repeat, this entire PDE is getting converted to FDM. FDM, finite difference method, graphics in computer graphics.
Uh, yeah, first fundamental of calculus. Fundamentals.
Okay, but, or let me quickly again, let's go back.
Derivative and definition होता है.
Okay, so if let's say I'm taking a derivative of, let's say, a variable t with respect to x. Okay, so what I'll do is, I'm just taking a very basic intuition example. Okay, so let's say there is a rod. At this step, the rod is at 0 degree at the left end. At the right hand, it is at 100 degree, and I want to find out the distribution of temperature across this entire rod. Okay, what I can do is, definitely I can find analytical solution if I have the differential equation, and if it is solvable, I can find the analytical solution. Or what second way, the discretization way, what we prefer in computer graphics. Okay, I'll talk about that. Okay, so in computer graphics, what we can do is we can divide this entire rod into n samples. Okay, let me divide this entire rod into n samples such that the distance between two samples is, let's say the rod length is L, so it becomes L by N, the distance between two samples. Okay, or is it N plus 1? Let me think. It could, that's fine, right? Okay, so now this becomes the difference. Okay, my battery, the charger. सब देना पूरा plug देना पूरा कर देना.
But so the electronic slide I just take the samples and then derivative working minus divided एडी कॉलेज में माइनस का एक्सपोनेंशियल फॉलो टेम्परेचर ओके वो तो मुझे
समझ गए?
मटेरियल प्रॉपर्टी है फॉलो किया होगा।
यार मैं बंद कर रहा हूँ 1 मिनट के लिए, ये बंद कर रहा हूँ।
अरे प्रोजेक्टर बंद हो जाएगा मत
प्रोजेक्टर कैसे बंद होगा? ये ऊपर नहीं जाएगा बस। प्रोजेक्टर का तो कहीं और है ना। क्या क्या? हाँ मैक और ओके। You understood, right? What's FDM then? Okay, there's my. Yep. स्टाइलिस उधर रखा है क्या मैंने? स्टाइलिस दे दे। Thank you. Okay, so dt by dx you understood. Okay, fine, good. So what we'll do over here is again we discretize the entire surface or the solid or the curve. We'll discretize it. We'll apply FDM, and for time integration we use symplectic Euler. They have used symplectic Euler for time integration, and that's how they have animated the entire scene. Okay. Uh, Now let's talk about one final thing. What's the significance of this alpha eta? And then let's talk about what's the significance of beta and chi or she, whatever you call it. Okay. And that's it. Yes. Okay. I mean, if you want, you can go through it. But let's let me quickly show you that alpha. If alpha is positive, what this means, eta is always positive. If alpha is positive, then what this means is Gij is greater than Gij 0. Okay, it's greater than, the Gij is greater than Gij naught. Okay, since it's greater, we have to go towards Gij naught. So we are trying to shrink the length so as to reach Gij naught. So whenever the deformation, if the length has increased, then alpha value will be very high. And alpha negative means the deformation is towards the compression side, so that it should extend to reach its natural state. Okay. And comes your eta ij. Let's talk about what's eta ij. Then there's eta 1 1, eta 1 2, eta 2 1, because it's 2 cross 2 matrix. For a surface it's 2 cross 2 matrix. So what eta means we can see here. So I'll suggest once do go through it. I'm freezing myself, so can you just go through it. Okay, so as if you see eta 1 1 and eta 2 2, they determine the resistance to length deformation, and eta 1 2 and eta 2 1, they perform shear deformation. Okay, so I hope you know what's shear, mechanical people. Good. And same is the significance of beta and she. ये कंप्यूटर साइंस. ओके, तू तो है ना मैकेनिकल, कंप्यूटर साइंस. ओके, तो तू और मैं ही है सिर्फ. इलेक्ट्रॉनिक्स में, इलेक्ट्रोमैकेनिक्स, मेकाट्रॉनिक्स. Okay. Again, you can go through it, the significance of beta and she. Okay, so beta, I'll quickly tell you. So if you remember, when I talked about the curvature, if the curvature is high, means it's more curved. If it's on a straight line, then beta ij, bij, sorry, not beta ij, sorry, bij is 0. That's what I said, if you remember from my earlier diagram explanation, right? So now if beta ij is positive, what it means is that my natural state is less curved than my deformed state. My deformed state is more curved than my natural. So it wants to go towards that lesser curvature state. And when this beta ij is negative, my natural state is more curved. Okay, do you want me to repeat? It's fine, right? Okay, and yes, same goes with the shy ij. You can again go through it quickly. So it talks about the twist,
Isn't twist the same thing as the torque deformation?
the torsion, not torque. Torque is different.
Yeah, sorry, for the torsion, that's the same thing as the twist deformation.
This is
Yes,
for bending, right?
yes.
This is not for twisting.
It's not for twisting, but it will have the same effect as twisting in surface.
Oh.
इनसे पकड़ के ऐसे घुमा दिया.
Okay, and yeah, that's it from this paper. So by the way, when they performed experiments, so the external force, they added gravity, they added spring force, they added viscous. So what they did is on that the deformable object, the elastic object, they actually throwed a fluid on it
Oh,
while doing their experiments. So they have given the equation of the force which they used while doing the experiments. They have, by the way, also created experiment with an impenetrable object, the object which cannot be penetrated, and they have shown at least they have shown visual. They have not shown the video. They have just shown images. Okay, maybe in 1987 the videos were not there. Maybe.
Was likely than not.
Toy Story took 2 years to render.
Toy Story 2.
99.
Toy Story
95 है.
19 to 1992 93 में वो build हो रही थी. तो उसको 2 साल रेंडर किया तब 95 में.
Oh, ऐसा है.
Nice.
Okay, okay. Okay, so they have shown experiments and they have given the equations of all these forces in their paper. So they have shown experiments. And yes, that's it from my side. Any doubts? Let me.
I think जो हाफ वाला कॉन्सेप्ट है वो सही है क्योंकि जो बाद में वो जो नहीं आया जो शेल मॉडल आया थिन शेल मॉडल उसमें h/4 का फैक्टर
आप हमने अल्फा में डाल
हाँ
कांस्टेंट में घुसा लो आप. नो कांस्टेंट.
Okay,
उसमें घुसा दो.
okay.
वो तो उड़ा ही देते हैं.
Okay, I'll stop sharing.
Images है तो वो दिखा दो.
Images, okay. So let me restart sharing then.
बन गया तो दिया.
हाँ
समझ सकते हैं.
Okay, so yeah, these are the yes. So this is the sphere is impenetrable object. They have thrown it on this elastic cube, and this is how it looks like.
प्रिंट करके स्कैन किया. इफेक्ट देखो बैकग्राउंड बड़ा अजीब सा नहीं है. मुझे लग रहा है ना प्रिंट करके भी स्कैन किए
हाँ
बेटा.
वही क्या हुआ एक्चुअली मतलब उस टाइम से तो
इमेज फॉर्मेट ही नहीं थे क्या तो.
इन्हें एल्गोरिथम दिया था
नहीं.
नहीं बता एफडीएम का बताया था वैसे.
FDM, हाँ FDM. So they have.
इनने ऐसा तो नहीं किया पेपर में नंबर्स निकाल के फिर उसको उससे हाथ से प्लॉट करके
ये तो नहीं इम्प्लिसिट स्पीड बताइए उन्होंने वही अपनी सिंपलिफाई वाली.
87 40 साल पुराना.
Okay. So should I stop recording? Okay. Fine.
So this is the first paper that shows thin shell model.
कैसे बोलूं इस टाइप की इक्वेशन बहुत सिंपल थी इनकी तो. देखो ना हमारी इतनी कॉम्प्लेक्स बन जाती पता नहीं वो क्या क्या जाएगी. इसके डेरिवेटिव लेने में अच्छा लगेगा. तो ये क्या करते हैं एक तो इनके अप्रोक्सीमेशन भी लीजिए ऊपर जाना
Hmm.
और ऊपर रुको ही रुको. हाँ ये वाली अनफॉर्चुनेटली बता रहा हूँ.
ओके ये सेकंड फंडामेंटल फॉर्म है ना
हाँ कुछ अप्रोक्सीमेशन लगाइए इसमें भी.
सो बेसिकली वो इसके मतलब एग्जैक्ट तो जो थिन शेल वाला पेपर था उसमें इस अप्रोक्सीमेशन की बात करी हुई है इस टाइप की
अच्छा.
सो जब सेकंड फंडामेंटल फॉर्म को डिराइव कर रहे होते हैं तो इट्स बेसिकली dr ट्रांसपोज dn, सो हाउ द tangent is changing along the normal. तो उसके लिए एक ही जरूरत पड़ती है फर्स्ट फंडामेंटल फॉर्म की।
अच्छा
तो
हाँ फर्स्ट फंडामेंटल फॉर्म आ जाता है।
हाँ।
तो दो टर्म आते हैं ना, क्योंकि वो डबल डेरिवेटिव है, एक वो डेरिवेटिव इनटू डेरिवेटिव वाला और एक डेरिवेटिव का दो बार
यस
हाँ स्केलर का दो बार डेरिवेटिव।
सो इट्स दैट उसकी बात कर रहा हूँ। यप हाँ, सो बेसिकली
हाँ,
यू वांट टू कंप्यूट द वेक्टर अलोंग द नॉर्मल, सो उसमें फिर तुम जब फर्स्ट ऑर्डर अप्रोक्सीमेशन ले लोगे तो तुम्हें ये मिलेगा इजी इक्वेशन।
ये क्वेश्चन प्रोटीन दिखा ना क्या कर रहा है उसके अंदर, जो उन्होंने अप्रॉक्सीमेशन ले लिया था। अच्छा तो उन्होंने स्क्वायर हटा दिया क्या नीचे? हाँ
नहीं स्क्वायर नहीं, स्क्वायर वाला सही है।
तो
जब तो उसका डेरिवेटिव लेगा ना, तो दो डेरिवेटिव एक है। अच्छा वो खुद ही डेरिवेटिव है ना बी जो है,
हाँ ठीक है।
तो जब तो उसका डेरिवेटिव उसमें चेन रूल लगेगा तो दो टर्म्स आएंगी, एक टर्म उड़ा ली उसने ऐसे है ना, एक टर्म उड़ाया था।
सो बेसिकली वो करते क्या है ना कि इसमें जो किया है बट हाँ वो
बी आई से डेरिवेटिव जाएगा वो निकाल दिया, जो डेरिवेटिव आएगा बी आई से का वो निकाल दिया।
बी इटसेल्फ भी और
तो नीचे उन्होंने वो जस्ट बी आई से ले लिया ना, तो बस डेरिवेटिव निकाल दिया उसका बी आई से का।
क्या
मतलब उन्होंने बी आई जे माइनस बी आई जे जीरो का स्क्वायर था ना, जब डेरिवेटिव लेंगे तो
बी आई जे खुद
आई आई जे बी आई जे माइनस बी आई जे जीरो इंटू डेरिवेटिव ऑफ बी आई जे आएगा ना, तो वो डेरिवेटिव ऑफ बी आई जे निकाल दिया।
बी आई जे खुद भी डबल डेरिवेटिव है।
इनकी सेकंड फंडामेंटल फॉर्म की फॉर्मुलेशन थोड़ी अलग है। del 2r by del x2 सॉरी del 2r हो जाएगा डॉट n है, and जो हम पढ़े हैं वो dr डॉट डॉट d है। See? मतलब एग्जैक्टली नहीं दिख रहा है क्योंकि वहाँ पे नॉर्मल जो क्रॉस प्रोडक्ट है उसका डेरिवेटिव का डॉट प्रोडक्ट है और उसमें नॉर्मल का डेरिवेटिव नहीं है। आई डोंट मे बी
ये दोनों फिजिकल मीनिंग तो सेम ही आ रहा है।
फिजिकल में
है ना, इसमें भी हमने वही किया, रेट ऑफ चेंज ऑफ टेंजेंट और फिर नॉर्मल के डायरेक्शन में।
ऐसे हो सकते हैं कि लेट्स से यू हैव अ मिड सरफेस एंड you are trying to define the curvature of a surface and then अब let's say वो flat था और अब उसको मैंने ऐसे कर्व कर दिया विदाउट शेल। ये तो जो मैं बोल रहा हूँ पूरा शेल को अज्यूम करके बोल रहा हूँ कि सॉफ्ट शेल
शेल तो हटा लो,
शेल की तो बात ही नहीं करता ना।
शेल भी तो मिड सरफेस पे आते हैं ना घूम करके से।
हाँ तो फिर मिड्स नहीं, बेसिकली शेल में जब हम बात करते हैं ना कर्व के कैसे कितना बेंड है तो इट्स द अमाउंट की अगर ऊपर वाला सरफेस है मिड सरफेस के वो कितना एक्सटेंडेड है।
उसको छोड़ दो ना, आप शेल में एक दूसरे तरीके से सोच लो कि मैं कर्वेचर पेनल्टी लगा दी तो उसमें तो 2D प्रॉपर 2D शेल पे भी वो भी वापस आएगा अपने इनिशियल शेप पे। इनका अच्छा वहाँ पे शायद यही था, वहाँ पे वो लेते हैं ना स्ट्रेचिंग,
वो बेसिकली जो डिफरेंस है उनका
हाँ, ये क्या
वो
बोलते हैं
कंप्यूट करते हैं तो उसको लेकर थोड़ा सा फंडामेंटल फॉर्म
से ये तो बेंडिंग। हाँ तो बेंडिंग स्ट्रेस जो बढ़ता है वो तो इंडियन शियर भी होता है।
तो इसमें पता नहीं सोचना पड़ेगा डी आर कर्वेचर अलोंग द नॉर्मल।
ये क्वेश्चन कैसे जाएगा 15 कैसे मैच होगा?
Okay, fine. I'll.
रिकॉर्डिंग बंद कर लीजिए।
Okay, so I'll be uploading it on YouTube, ठीक है? So वहाँ पे questions अगर है तो पूछ लेना।